Hello everyone, and welcome to the first video of the Introduction to Electronics with Arduino IDE playlist. In this series, we'll be going over the basics of electronics and covering various concepts and topics. This first video would be an introductory video into breadboarding and the layout of the Arduino Uno. So without further ado, let's get started. So we're going to take a look at the breadboard first, and the important thing to know about these solderless breadboards is how the pins are connected. As you can see, each breadboard has a series of holes that are arranged in two distinct ways. So over here we see that there are holes that are arranged vertically from my point of view, and there are holes that are arranged horizontally. The horizontal arranged holes are always at the edges of the board, so these two edges, and they have this plus and minus symbol as well as this colored line. On the other hand, the holes that are arranged vertically from my point of view are much smaller. They are only 5 holes in length, and they are also labeled with number. So we have 1 over here and 30 over here. So the important thing to note is that the holes are connected, or the way that the holes are connected is vertical along these holes. So if we were to look at these columns from 1 to 30, so this would be connected to this, would be connected to this, would be connected to this, and likewise this would be connected to this, would be connected to this, would be connected to this, and would be connected to this. So these two are not connected, so 1 and 2 are not connected, but 1 is the entire column over here. All of these holes are connected to each other, and likewise for 2. So we can think of it as multiple or 30 parallel columns, parallel vertical lines that are all connected to each other. So this will be connected, this will be connected, this will be connected. Hopefully you get the idea. So let's illustrate this with an example. If let's say I were to connect, so this over here is the single core 22 gauge wire, which you can get quite cheaply from online stores. So if let's say I were to place one of these pins into this hole, and I were to place another pin into this hole, what I'm doing is I'm connecting the whole of this column, which is 1, to the entirety of this column, which is 5. So this would be, in some sense, a valid connection, because perhaps I have some component on column 1 and I'm going to connect it to another component on column 5. So what a negative example looks like is if I were to connect perhaps connect 2 pins of the same wire, or connect 2 ends of the wire to a single column. So in this case, I've connected both ends of this makeshift jumper wire onto column 1. And what this does is it essentially does nothing, because we know that column 1 is already all connected to each other. So this wire is in some sense pretty redundant, and it doesn't serve any purpose. Okay, so now that we've settled these, let's talk about these. So these horizontal, from my perspective, horizontal holes are all connected to each other in this manner. So similarly, let's say if I were to connect this and this, I would be bridging this entire row with this entire row. And these are not connected to any of these, and yeah, you get the idea. So what are these long horizontal rows for? Well, as the symbol suggests, these are used to create your ground and your VCC rails. So if you have a project that's running off 5 volts, say, and you would want to have many sensors, actuators, or whatever have you running off 5 volts, you would connect one 5-volt wire to this from your microcontroller or from your power supply, and then you would connect one wire from ground from the same power supply or microcontroller to this. And because this whole row of pins, or perhaps holes, are connected to each other, we can just connect things to any of these holes along the same row, and they would therefore be connected to this the first hole, and then connected to your power supply. So that's the idea. So the next thing I will talk about is what is this river or gap between these two, and this actually is a break. So it prevents this from being connected to this. So As I said earlier, that this entire row is this entire column is connected, but it does not continue across this river or across this bridge. Across this break, because this break is it signifies that there is no continuity between this column and this column. So a reasonable thing to do would be to connect. Perhaps I connect one end of this wire into this column, and then I connect another one into here. So this is a reasonable connection to make, because this column is not originally connected to this. So putting this wire here bridges these two, and it is a possible connection if you were to say we want to bring two pins of an IC to the same level or something like that. Alright, now let's get into unpacking the Arduino Uno board. So this over here is an Arduino Uno clone. It's not the original. It's a cheap copy that I got from China, but it performs almost identically, and it is essentially the same thing as the original Uno that you buy from the Arduino store. So over here on the Arduino board, you can see many pins. So these pins are how we interact with the board and how we get the board to do things, get the board to take readings of sensors, move servos, etc. Everything is interfacing through these pins. So if you have correctly deduced that these pins are identical to those on the breadboard, you are right. These pins are like the holes on the breadboard. We can take a wire and we can just stick into these holes, and the connections will be made. Okay, so let's now break down the Arduino Uno into the functional groups or functional regions of its pins. So over here we can see that we have one area of pins called digital, we have one area called power, and one area called analog in. So let's just start with the digital, because that's the most commonly used. Digital means we can have two values, 1 or 0, on or off, high or low, whatever you name it. That's the idea of digital. It's binary, it only has two values. At least that's what that's what we need to we should think of. Of course, there are special ways we can create levels, or we can make analog outputs using something that's known as PWM. That will be in the next video. But for now, let's just think of digital as only having two values, on or off. Okay, so that's for digital. So these pins can input or output a digital value. So it can either output high, which is most commonly 5 volts, which is the supply voltage you supply to the Arduino Uno, or it can output 0, which means that it outputs ground, which is 0 volts most of the time. So this is what digital pins do. So if you were to attach a sensor, say, or perhaps let's think of it, let's choose something more applicable like an LED, we can turn it on by by outputting high, or the output voltage on one of these pins, and then turning it on, and then turning it off by outputting low, which is ground, or 0 volts, so the LED turns off. We can also measure things such as buttons, because a button is a digital device because it only has two states, either on or off, or pressed and or not pressed. So we can measure if a button is pressed, we can, record the value on a pin, and when the button is pressed, that value changes, and we can do stuff with that. So that's for another video as well. So that's the basic idea of digital pins. Now moving on to the analog pins. Analog is something that is it's like the converse of digital, where you're not limited to just two values, you have a range of values. So for instance, on the Arduino Uno, we have a range from 0 to 1023. How do we get that number? It's because of something called the analog to digital converter, which is to put it simply, it's this device that converts analog or variable, like multi-level voltage values, into digital values, which is what the microcontroller can process. So this is a 10-bit ADC, which means that we have a resolution of 2 to the power of 10, which is 1024. And this means that when we record a value on the analog pin, we get a number between 0 and 1023. The important thing to note is that this is strictly analog in. So this is only an input. These pins are only input. You can't output analog value. You can't tell it to say like output 2.5 volts or some voltage that you choose. That's not going to happen. It's only going to read values. So that's very important because it's analog in. Okay, so what could you use these pins for? You could use them to measure the voltage across a resistor. Perhaps it's a light-dependent resistor that changes resistance with light intensity. It could be a thermistor that changes resistance with temperature. You could also measure the value, the voltage across a potentiometer, and that changes with resistance as you twist the knob. There are various things you could use, but the important thing to note is that analog means there are more than one or more than two values, a range of values, which is actually what we as humans experience in our daily life. We don't see things, as one or zero. We see things as a range, light intensity, temperature, sound levels, stuff like that. So that's how we can use these pins to interact or interface with our real world. Okay, the last thing that we need to take note is power. So eventually the Arduino Uno is an electronic device. It will require power to operate. So over here we see a bunch of pins. We see V in, ground, 2 grounds, 5 volts, 3V3, and reset and 5 volts. So ground is quite self-explanatory. It's where all the conventional current goes, and you have to have, if you build a circuit, you must eventually you must provide a path of return for conventional current to come to ground. V in is a bit interesting. It's actually connected internally to this DC, I think it's a 2.5 barrel jack, which accepts, I believe, up to 9 volts. I might be wrong on this, but the idea is that you can supply voltage between 5 to maybe 4, I think 5.5 to 9 volts or so, and it will convert it down to 5 volts. So this pin can be sort of used as a power input for sources of voltage that are not exactly 5 volts. And you could then let the onboard voltage regulator, which is like this step down device that converts the voltage down into 5 volts, do the work of converting that into 5 volts. But I wouldn't recommend that because the linear regulator that this uses is not very efficient. It would generate a lot of heat, and it just isn't very power efficient. It will waste a lot of energy in the process. Okay, so that's V in and ground. 5 volts is, as you have expected, it's the 5 volt rail, or it's the 5 volt source where the chip gets 5 volts from and where your electronics will get 5 volts from if you power this via the USB, because USB is the voltage of USB, or the supply voltage of the USB is 5 volts, so the 5 volts will come out over here. 3.3 volts is quite similar. The idea is that you will drop this 5 volts back down to 3.3 volts. Once again, I don't really recommend using the 3.3 volts as like a power source to get power out, because the 3.3 volts on this chip is taken from the CH340 that has this sort of like a 3.3 volt reference. I don't really think it's suited for drawing, powering things from that reference, but I might be wrong. Nonetheless, it's really not a good idea, since the CH340, this chip is not really meant as a power supply. It's more of a USB to serial converter. So it's best to get your own power supply that drops the 5 volts to 3.3 volts and use it from there. Reset is more for the communication, it's more for controlling the board in terms of resetting it so that you can upload code, resetting it so you can rerun a program. So this is also connected to this button, which is the reset button. Pressing the button will actually pull this pin to ground, and that will trigger a reset of the board. So this usually isn't really used in projects unless you want to have another microcontroller like externally reset your chip. Then perhaps you might use this. And last but not least, we have another 5 volts, which is essentially just connected to the 5 volts over here. Alright, so we've talked enough about the basics of breadboarding and the layout of the Arduino Uno. Let's actually start to do something with them. So the very first circuit I'm going to build is going to be the simple always on LED. So this is going to just be an LED that turns itself on when we plug in the power and stays on for the entire duration of our entire duration of when the USB is plugged in. So it has no code whatsoever. It's just a dumb LED. So how are we going to do that? Let's just draw our simple circuit diagram first. So a quick introduction to circuit diagrams for those who are not familiar with them. There are various symbols that we use to represent our components. So the symbol for an LED is this triangle, and then perhaps some arrows to show that it emits light. This is a LED or light emitting diode. And a resistor, it can either be this, a box with two things sticking out, or it can be a squiggly, a jagged line like this. So depends on which country you're in, which system of symbols you subscribe to. This is the standard depiction of an LED and a resistor. So that's all we need to know for this simple circuit. Okay, so let's start to draw our circuit. So we start with our 5 volts. So this arrow is usually just to show that this is a voltage point or a voltage source. And so 5 volts, we're going to put our resistor, and it's going to use this format because my country actually uses this format, but perhaps the tools that I use a different format, but let's just use this format. I'm going to put the LED like this, and I'm going to put it to ground. So this is ground. This 3 lines shows depicts ground, and this upward facing arrow with plus 5 volts depicts 5 volts. So very simple circuit. It just means that the LED, this current is going to come through from 5 volts to this resistor, and then it's going to go to the LED, light it up, and then go to ground. So that's pretty cool, right? So there's only one question, which is how do we calculate the value of R? Because we know that a resistor can have various resistance values. So we got to, think of what value do we use. So for those who may have done a bit of electronics before, and this circuit is not new to you, you might be you might know that the value is between 100 to 200 ohms. So this is a widely accepted value. Actually, it can be higher. It can even go up to 1,000 ohms. The LED just gets very dim. But how do we actually arrive at this value? So the first thing we have to do is we have to go back to our basics, which is actually just Ohm's law. So Ohm's law states that the resistance is equals to the ratio of voltage is to current. So that is basic Ohm's law. And how does it apply to our example here? So we need to know some specs or specifications of our LED. So let's just assume that this is a standard 5mm LED. In fact, let me just take one out right now so you get the idea of what the LED actually looks like in real life. So a typical 5mm LED looks something like this. It's just a little bulb. It has 2 prongs, and you pass current through the 2 prongs and it lights up. So this is how an LED looks like. This is a 5mm LED. It's really cheaply available from various online stores. And that's what we're going to use today. So what are some specs of the LED? So our LED is, let's just say that most of these LEDs have a forward voltage. So what is forward voltage? It's something like when the LED is operating at the correct conditions, you would notice a 2 volts drop across the LED. So 2 volts will drop across LED. It can be more, it can be less. I just estimated this value, but it's usually around there. 2.2 volts, maybe 3 if it's a really high power LED, but usually 2 volts is a very reasonable guess. Okay, and we know that the average current going through an LED, well, it's between 25 to 50 milliamps. So that's also just a number which I have estimated. I didn't actually refer to the data sheet of the LED. You should if you are really particular about this, but I would suggest that, just take an estimate and just use that to make a rough guess, and then you round up and down based on what you have. So with these values, we can actually calculate the correct or the appropriate resistor value to be used for this resistor. So with this in mind, we know that R equals V over I. So what will be the voltage drop across the resistor? Well, if 2 volts drops across the LED, then since voltage in series, it adds up. So 5 volts is across this whole thing. So therefore, this should be around 3 volts. So 3 volts will drop across the resistor because 3 plus 2 is 5. Okay, we know that. Next, we know that the current through this LED has to be between 25 to 50 milliamps. Okay, so current through a series circuit is constant because the electrons only have one way to go, the current only flows in one direction. So if the speed of electrons along this path has to be the speed of the electrons along this path. It's like if you have a bunch of cars on the road, the speed of the cars is going to be the speed of the slowest car, assuming that the slowest car eventually becomes the car that bottlenecks the entire road. So if the current going through this LED is 25 to 50 milliamps, the current going through the resistor is also 25 to 50 milliamps because this is a single continuous path. Okay, so now we know what voltage goes across the resistor, which is 3. We know what current goes through the resistor, 25 to 50 milliamps. We can actually calculate the appropriate resistance value. So R equals 2, and the voltage we know it is going to be 3, and the current value, let's just take the smallest, or let's take the biggest value so we know what is the smallest value of resistor we can use. So then we can choose something that's slightly larger. So let's just say 50 milliamps. So that's 10 power to negative 3. And I'm not that good at quick math, so I'm just going to use my calculator for a moment to get the answer real quick because I'm not extremely fast at this. 60 ohms. So 60 ohms is the lowest value because this is the largest, so therefore this will be the smallest. So this is the lowest value, and actually let's, for the sake of practice, let's actually calculate the other value if we assume that the current is 25 milliamps. So 3 volts over 25, 10 minus 3, that would give us 120 ohms. So as we can see, the range is between these. So this initial estimate, or this initial rule of thumb, actually is quite relevant. I mean, 60 is around 100, you know, give and take. We don't actually know the actual voltage, the voltage drop because LED, we don't actually know the current. This is just an estimate. But using a value between 100 and 200 to 200 should do the trick most of the time. If you use more, that works too, just the LED gets really dim. And if you think about this Ohm's law thing, it would be a lot smarter to just put a much higher value than needed, because if your value is too high, your LED just doesn't turn on. If it's too low, because we can also reverse this equation as I equals to V over R. If your R is too low, then I gets too big, and you risk burning your LED. So we always try to go with the safer side, which is to have a high resistor value than to choose a lower resistor value. Alright, it's time to start working on the circuit. So I've gotten myself a bunch of things. Of course, I've gotten my Arduino Uno, my breadboard. I've taken a bunch of these single core 22 gauge wires. I've gotten a 100 ohm resistor, an LED, and of course, I've gotten myself my trusty multimeter. So we're going to use this multimeter to test the circuit before we actually power anything up, because we don't want to have silly mistakes causing our hardware to burn or to explode or whatever nasty things can happen when you short circuit stuff. So the first thing we're going to do is take a look at our schematic. It's a really simple schematic. So 5 volts and then resistor and then LED. Okay, so the first thing we do is I'm going to take my red wire, because red is usually associated with supply, and I'm going to put it to 5 volts. So I'm going to zoom in here for a bit. Alright, so we can see the first pin over here corresponds to this random unused pin. Then its second pin goes to 5 volts, third pin goes to reset, fourth pin goes to 3.3 volts, and fifth pin goes to 5 volts. So I'm going to put my red wire into the 5 volts, which is the fifth pin. So 1, 2, 3, 4, 5. And then that will go into this plus rail. So as I mentioned earlier, this entire rail is connected to each other. So whenever I connect anything else to these pins, it will also be connected to 5 volts. Okay, now I'm going to take my black wire and I'm going to put it into ground. So ground is just the next door neighbor to 5 volts. So it's going to go in here, and I'm going to put it into the ground pin. So that's going to be here. Oh, that's tough to put it on camera. Alright, we did it. So that's going to go to ground. Okay, so next we're going to put our resistor, and that's going to go from 5 volts and it's going to go into our LED. So how are we going to do that? Okay, we're going to take our resistor, we're going to put it into the 5 volts, which is the plus rail. So as I said, any pin along this rail will be connected to 5 volts. I'm just going to stick it into any random column because I don't have anything else on this board, so I can take all the real estate I want. Then I'm going to take my LED, and we can notice that the LED has 2 prongs. It has 2 pins. It has this longer one and it has this shorter one. So the longer one is positive, or perhaps more specifically, the longer one is going to be this area over here, the anode, if I'm not wrong. Yeah, this interesting way LEDs are named. The anode, and then the shorter one is going to be the negative side of the cathode. So I'm going to take the LED, the longer side is going to go into the resistors column, which is going to be 7. So it's going to put it in, and the shorter one can just go into the one next to it, so that will go into 8. So I'm going to plug it in like this. Once again, I'm going to double check the longer one is indeed going into the resistors column. It does. Let's go. And then I'm going to take this green wire and I'm going to bring it back to ground, because as per the schematic, everything has to come back to ground. So this can just come over here and go into ground. So there we go. Did I make any mistakes? I don't think so. So okay, hopefully this works. Okay, so before we plug everything in, let's actually do some safety checks. So the safety check we're going to do is that we're going to actually check that we did not short circuit our 5 volts to ground. This is because if we did, a lot of current would rush through 5 volts to ground. It could potentially burn our chip and maybe our computers, a USB port, and a lot of nasty things happen when that happens. So I'm not going to run the risk. I'm going to actually test to see if it's connected. So I'm going to turn my multimeter dial to this symbol, which is the diode symbol with the sound wave symbol. That is a continuity test. It will test if things are connected to each other. So if I put these 2 prongs together to simulate a short circuit, you hear this loud beep. That is not good. We do not want to hear that. Okay, now I'm going to put this onto here, and I should see a number. Yep, 910. Oops, slipped. 910, no beep. That's good. We know that we did not short circuit anything. I can take my multimeter, put it away because we won't be needing it. And I can take my USB cable. I've already connected it to a power source, which is a phone charger, and I can just plug it in. So as you can see, the LED lights up, everything works. And that concludes the very first session of our series. Take care, happy hacking, and I'll see you next time.